Get it? We have a submerged pump that takes water from a lake and delivers it to a storage tank. So I'll make some sketch. Here's a lake and the water level in the lake like this. And you put a pump somewhere in the lake such that the pump is submerged. The inlet to the pump is submerged and the outlet comes out. Maybe it goes along here, maybe it goes here, and then finally it spits it out. The water gets spit out at the end of the pipe and it's collected in a storage tank that's at a higher elevation. But the pump is submerged and the inlet to the pump is submerged 6 meters below the water level in the lake. So if I wanted to introduce, I would say this depth here is 6 meters. The outlet is 85 meters above the lake water level, not above the pump, but above the lake water level. So the outlet is 85 meters, and it discharges into the air. So it's just going to be spit out that pipe, and then it would fall into another tank. The water flow rate's given to be 11 kilograms per second, and the pipe diameter everywhere throughout, the inlet pipe diameter, the outlet pipe diameter, everywhere throughout, there's just one diameter for the pipe, and it's 6 centimeters. Assume the water is incompressible. Even if they didn't say that, I would assume it. And as constant temperature throughout the system, even if they didn't say it, it's typically the water's not being heated up as it's being transported. It's constant temperature. Determine the power required to run the pump. So we have some power to go into the pump. And let's put it W dot in. Units, watts or kilowatts. That's power that goes into the pump. How would I calculate the power to go into the pump? Introduce the control volume. Here it's not so clear where the boundary of the control volume should be. But let's do this. I'm going to cut the boundary of the control volume where it's discharging. And so it's going to be discharging out that outlet pipe. So that's one place where the boundary of the control volume needs to be at the outlet to the pipe. And then we'll enclose the pipe. And it needs to cut so that it's the work coming into the control volume or the power coming into the control volume to run the pump. So we cut it there. And then it takes a little bit of judgment to put the other boundary. I'm going to do this. I'm going to put it an inch or a half an inch or a couple millimeters or something like that below the water level in the lake. And just go on and on and on. All right? And here, go along the bottom of the lake, and then finally it'll come up along the other edge of the lake. So, along the bottom of the lake, is there any mass flow of water coming into that control volume? Nope. Nope, nope, nope. Along the air, is there any mass flow rate coming into the control volume in the air around the outside of the pipe wall? Nope, nope, nope. But we do have an outlet right here. We have shown that. So that's a m dot exiting. And where's our m dot coming into the control volume? The 1 inch, half an inch, couple millimeters below the water level. It's just falling into it. So it's coming in all along the top surface. True? All right. Now I'm going to be introducing some states. Let's call this state 1. Where is that? What's coming into the top of that control volume at the surface of the lake water? Okay, that's the water coming in. Okay. Where is state 2? Right at the inlet to the pump. That's state 2. Where is state 3? Immediately at the discharge of the pump. And where is state 4? At the discharge of the pipe. That's the high elevation. So I have state 1, state 2, state 3, state 4. and a very clearly defined control volume. All right. So let's do this. Let me summarize some information. State. I'm going to talk about 1, 2, 3, 4. 4 states. Let's talk about the elevation of each of these states in meters. Well, I had to pick some place to start measuring it from. I could measure it from sea level. But let's do this. Let's measure it from the pump. Pump is at Z equal to 0. So state 2 and state 3 have 0 elevation. What's the elevation of state 1? 6 meters. What's the elevation of state 4? Think about it for a minute. 85 plus 6. All right, that's good. The speed of the flow in meters per second, that's a bad looking second, at those locations. The cross-sectional area for 1 is very large, the surface of the lake, but it's a little bit below the top surface of the lake. So what is the velocity of the water cutting into the control volume across surface 1? 0. Approximately 0. Negligible speed. True? Isn't the speed at 2, which is a 6 centimeter pipe, and the speed at 3 and the speed at 4 all the same? They're all the same. And how would I calculate it? Well, I know the mass flow rate, 11 kilograms per second. I multiply by the specific volume. That gives me a volumetric flow rate. And then I divide by the area of the pipe. Or maybe you just remember m dot's equal to AV divided by the specific volume. I need to solve for V. Well, without going to the tables, what's the specific volume of water? 1 over 1,000, 0.001. What's the density of water? 1,000 kilograms. So this is 0.001 meter cubed per kilogram, and this is 1,000 kilograms per meter cubed. Good. I trust that we can calculate that velocity, and I will save some board space and say that that comes in at 3.89 meters per second. 3.89 meters per second. 3.89 meters per second. That's the speed at those 4 places. Okay. Pressure. What would be some good units for pressure? Pascal? Kilopascal? Kilopascal or Pascal? Let's put kilopascal if we like to work in kilopascal. That's great. What would be the pressure at state 1? 0 gauge or 1 ATM? We could solve the whole problem in gauge, or we could solve the whole problem in absolute. It's probably the first time you do this, you probably should do it like this. I don't know. Put P in kilopascal and do it both ways. This will be in gauge, and this will be absolute. Okay? What is the pressure gauge at 1? 0. What's it in kilopascal at 1? 101.3, 1 ATM, 101.3 kilopascal. All right. Well, what about the pressure at 2? Oh, I have to do a little work to get it. How about the pressure 3? I'll have to do a little work to get it. What about the pressure at the outlet at 4? Same as 1. It's atmospheric pressure. Water's just coming out the end of the pipe. It's 0 gauge, 101.3 kilopascal. True? All right. That'll help us a little bit as we organize our thoughts. For this control volume, if I do an energy balance for this large control volume, I'll have W dot coming in, and notice that I abandoned the sign convention with my illustration. It's into the control volume. I'm putting it in as a positive. I don't like a lot of negatives. All right. Is equal to the mass flow rate times the enthalpy 4 minus H1. It would be 1 minus 4 if I left it in this traditional. And then I'm going to have the specific kinetic energy out minus specific kinetic energy in plus the potential energy out minus the potential energy in. Do you agree? The out is 4, the in is 1. Let's expand this. It's going to be U4 minus U1 plus P4 minus P1 times V plus 1/2 V4 squared minus V1 squared plus G times, and I didn't really save enough room. Let me scoot that over just a little bit. All right. Times Z1 minus Z4, minus Z1. I'm going to pause. Is it clear? Did I make an algebraic error? Are we okay? Now let's cross some terms. Why is U4 minus U1 0? Constant temperature. It's incompressible. U is a function of temperature only. It's gone, right? All right. Why is P4 minus P1 0? They're the same pressure. We just talked about that, right? Okay. What is V1 0? So what I'm left with is the statement that says the power that I have to supply the pump is proportional to the mass flow rate through the pump. If I'm putting a lot of fluid through the pump, I'm going to need a bigger power source, a bigger motor to drive it. Okay? Times, I'm going to have G times Z4 minus Z1. How far am I going to lift it in the gravitational field? Is Z4 a lot greater than Z1? I'll need a bigger pump, more work to lift it higher. Plus 1/2 V4 squared. It's got to spit it out the end of that pipe. And that's kinetic energy. I have to supply work to spit it out the end of the pipe. So we can read these equations, can't we? So let's now see about substituting some numbers. 11 kilograms per second times 9.81 times Z4 minus Z1 is 85. Plus 1/2 V4 3.89 quantity squared, and everything inside that bracket has meters squared per second squared as the unit. I know I'm trying to save space, but the V is the meters per second. I square it, it's meters squared per second squared. I look over here, I G 9.81 meters per second squared, but I multiply it by Z, which is meters. So I get meters squared per second squared. True? Unit conversion, what's Newton? Newton is a kilogram meter divided by second squared. So there goes the second squared. True? And then what did we have? We had a joule is a Newton meter, so the Newtons went. And then we're going to get meters squared. You're left with joule per second, which is a watt. And so we calculate that this is the power in has to be 9,256 watts. Done with part A, okay? I don't want to erase anything on that page. I hope you have good notes, but I need to continue the problem. So I need more space. So let's do this. I want to just get rid of a lot of this stuff here. All right, that should work. True? So now let's go and solve part B. What is the pressure at the inlet to the pump? Do this. Introduce a new control volume. What control volume would be helpful? Maybe I'll sketch it in color green. Come along here where it has the same boundary along 1, but then come down and cut right there at 2. And so the only 2 places there's water flow into that green control volume is at 1 and out at 2. And now we'll do conservation of energy balance for that control volume where there's only 1 and 2 on the inlet, right? Is there any shaft work for that control volume? Is there any W dot cutting across the boundary of the control volume? None. So what we have is 0 is equal to the mass flow rate. Let me back up a little bit. Here's the energy balance. 0 is equal to the mass flow rate times U exit 2 minus U inlet 1 plus P2 minus P1 times V plus 1/2 V2 squared minus V1 squared plus G times Z2 minus Z1, close parent. That's our energy balance. There's no work, it's steady state, 1 inlet, 1 outlet. I then cancel m dot from the equation. Just divide the whole equation by 1 or multiply by 1 over m dot. 0 on the other side, so it goes away. We have the change in internal energy 0. We have, what about the inlet velocity? 0. And we're interested in calculating P2. True?
P1 is 0, right?
P1 is either absolute or gauge. If you're working gauge, it's 0. If you're working absolute, it's 101. So let me do this. It's equal to P1 minus, here, do it plus. Plus, I'm going to do a rho G Z1 minus Z2. I switched the Z1 and Z2 to get the minus sign to turn it into a plus. Minus 1/2 rho V2 squared. Now, I'm going to pause. I want you to make sure that you like that algebra or that you don't like the algebra. Fix it. Now, I can read this equation. If I want to work in gauge, P1 is 0. True? If I want to work in absolute, it's 101 point, so there it is, 101.3. Look at, it increases because you're going down, and so Z1 is higher than Z2. That's the primary cause for having a higher pressure at 2, at the inlet to the pump. But why do we have a negative sign? Because it's having to be sucked into the pump, and it has kinetic energy. And the lower pressure is due to that kinetic energy component. So we can now calculate. We get 101.3 kPa plus 1,000 times 9.81 times 6 meters plus, minus 1/2 of 1,000 times 3.89 squared. And what we pick up is that it's 101.3 kilopascal plus 8.86 kilopascal minus 7.57 kilopascal. So this is atmospheric pressure at the surface. That's the hydrostatic pressure. And then I have this reduction because of its suction into the pump, the kinetic energy part. So the final pressure at state 2 is, depending how you write it, 152.6 kilopascal absolute, or it's 51.3 kilopascal gauge. Either one works. Only box 1 though. Right, don't give me too many answers. All right. All right. Ready for the next part? The next part says, what is the pressure at the outlet of the pump? The pressure at the outlet of the pump. Is it high, low, or what? What's the purpose of the pump? Increased pressure. So the pressure is going to be highest at that pump. So I should have put in 2 here. Maybe I put in 51.3 gauge or 152.6 kilopascal. How am I going to do it to calculate the pressure at 3? Let me do it this way. You can do a control volume that cuts it at 3 and it goes from 1 around the pump and cuts it at 3. That's fine. Another way to do it is do it with a control volume that cuts at 4 and cuts at 3. Let's do it for that control volume that cuts at 4 and 3. All right? We're going to do that at the very end. Yes, we're going to do that. But you would have to know the work first. You'd have to know that power of the pump, and we did get it from Part A. You're right. So there's 3 choices, but let's go with this last choice. So we're going to get that 0 is equal to the final exit U2, U4 minus U3 plus P4 minus P3 times V plus 1/2 V4 squared minus V3 squared plus G Z4 minus Z3. Hopefully I fit it all on the line. It's conservation of energy. Got rid of the m dot. There's no shaft work. So why is this 0? Same temperature. It's incompressible. What about why is that 0? They have the same speed. They're both in the 6 centimeter diameter pipe. So there's no need to accelerate it. The change in kinetic energy has the same kinetic energy. And so what do we pick up? We pick up P4 is equal to P3 plus rho G Z4 minus Z3. The only difference between the pressure at 3 and pressure at 4 is neglecting frictional flow in the pipe. I know no pipes are not completely frictionless, but it's like having a frictionless pulley in statics. Well, we can have frictionless flow in pipes in Thermo 1. And when you get to fluid mechanics, then you'll have the skills to account for the pressure drop pushing flow through the real pipes that exist in this world. Okay, so what you do is you put in your numbers and you find that the exit pressure, did I write P4? This is P3 and 4. Does that look better? So what do we have? We have 101.3 kilopascal. And then what is the elevation change? Z4 minus Z3? It's 91 meters. 91 meters. And so then that comes in at 893 kilopascal, or a total of 994 kilopascal. So 994 or 893. So looking at the pressure, it's very high at the outlet of the pump. That's the highest pressure. Okay, I'll try and tuck it in this space right up here. What is the pressure increase across the pump? The delta P across the pump, that's just the pressure outlet minus the pressure inlet. And that pressure change across the pump is 841 kilopascal. Somebody suggested we could do a different control volume. If you now say, what is the power into the pump, just focusing on a small control volume that cuts at 2 and cuts at 3, the kinetic energy in at 2 is the same as the kinetic energy out at 3. The potential energy at 2 is equal to potential energy at 3. It's just simply going to be the mass flow rate times that change in the pressure times the specific volume. You'll get the exact same answer, 9,256 watts of power in. There's more than one way to solve a problem. A lot of it depends on your selection of the control volume. Be careful. Be careful, and be not just careful, but be clear about your control volume. All right, let's move on.